I'll start by asking you about the spelling of laser. I mean, what would happen to me if I were to spell laser, Lazer, in one of your exams?
Laser, I mean, although we bandied the word around, laser actually stands for something. So laser is an acronym. So laser stands for light amplification by the stimulated emission of radiation. So the S is important because it stands for stimulated.
So what does this definition mean? Is there any way you can explain?
Yeah, well, we'll try. We were talking earlier about how energy was stored in molecules and rotational energy levels or rotational energy levels. So these energy levels exist in atoms and molecules. It's a little. This is all the quantum weirdness stuff. So energy can't come in continuous amounts. Comes in lumps. But normally, molecules occupy the lowest lying energy states. And that means that when you shine light on them, they can absorb that energy, the light energy, and be promoted from a low-lying energy state to a high-lying energy state. And normally there are many more molecules in the lower-lying states than in the higher-lying states. But under certain circumstances, you can create a situation known as a population inversion, in which you have more molecules in the excited state than in the lower state. And that means that when light hits this molecule, instead of being absorbed, it stimulates, it emits more light. And so if you have that situation, then the stimulated light then emits even more and more and more, and you get a process of amplification. And that's essentially what happens in a laser.
So how does it work? Is it this kind of movement from energy levels up and down? Is that how you get your light?
Well, so in order to get this situation of a population inversion, that's not a natural state of affairs. So you have to do something to do that, to create that state. And the way you do that is you exploit a third energy level in the system, and you pump loads and loads of energy into that third system, into that third level. And that third level then decays into this intermediate level, which has to have certain properties. It has to be what's called a metastable state. And then you have to put that system in between two mirrors so that the light that's emitted bounces backwards and forwards and stimulates more and more emission. And that's essentially how the process works. Does that answer the question?
So how efficient is a laser then?
Well, when I started out as a graduate student, a very long time ago now, lasers had only been around for 10 or 12 years, and those early lasers were incredibly inefficient. So we used to have a laser that was something called an argon ion laser, and we used to put 15 kilowatts of electricity into it, and we would get 5 watts of light out of it. So incredibly inefficient. But these days, as you know, I mean, in for example, a laser pointer, you can get a laser from a small diode that you can power with a couple of batteries. So it's changed over the years.
So if I were to compare a modern laser to, for instance, one of those old filament light bulbs, which we've been banned from using, are they more or less efficient than one of them?
Okay, I think what you're thinking about is there's a very closely related idea to a laser, and that's a light-emitting diode. And you can make light-emitting. If you put a light-emitting diode between two mirrors, you can turn it into a diode laser. But we're now beginning to use light-emitting diodes as light sources, and they are very much more efficient than filament lights. And that's really important because something like 40% of the world's electricity production is used for lighting. So just by you think, well, just changing my light bulb really going to have an effect on energy usage, and the effect's enormous because a large fraction of the power that we produce is actually used to produce light. So doing that efficiently is very important.
But using lasers as a source of light, would that work?
Oh, it certainly would. You wouldn't probably you wouldn't
to light
need-
our homes and things.
Well, you wouldn't really want to do that because lasers have a number of properties, and one of the properties that they have, I'm sure, as you know, from using from a laser pointer, is that the light comes out as a very directed beam, which you wouldn't want for lighting your house. You want a diffuse source of light. So a diode is a better source of light for a light bulb than a laser.
Okay, so why are lasers perceived as so dangerous by kind of just, the general public? Everyone says they're kind of these dangerous things. You get these safety warnings and all these lasers that you buy. Why are they seen as so dangerous?
I've really never understood. I mean, it is true that, as I say, lasers have this property of having a very directed beam of light, and so that the real danger with a laser is because it's very bright. Is danger to your eye, to your retina. So you can have an accident very easily in which you essentially blind yourself. So there are, if you don't know how to use them, and they're sufficiently powerful enough, then there's a safety hazard. But as far as I know, only one person has ever been killed by a laser. And that was actually when they were moving it around. They were trying to put it on the back of a lorry. These old lasers were very heavy, and it fell off the lorry and fell on them.
So it wasn't actually the laser.
It wasn't actually the laser that killed them. It was the power supply.
Right. Okay. Well, why are most lasers that kind of we see and we buy red in colour?
That comes about, as we were talking about this population inversion. To maintain this population inversion, it's much easier to do it if the energy gap between the excited state and what's called the ground state is small. And that's because the rate at which light is spontaneously emitted from atoms and molecules is a very strong function of this gap between the energy levels. So it's very much harder to do in the blue and in the ultraviolet than in the red and the infrared.
So why can you buy some lasers from the coins in your back pocket while others will cost you thousands and thousands of pounds? What's the difference between expensive and cheap, and why is there such a large range?
Well, it depends what you want to do with the laser. So for our consumer electronics, like our CD players and so forth, obviously, you've got the ability to sell millions of these things, and so there's a production costs. Whereas for some of the scientific lasers that we use, perhaps you might only make one or two. So, there's a difference there, and some, I think it depends what you want to do with it.
So, is there much of a general use for lasers within our society? Just for practical things.
Oh, but they're everywhere. I mean, every time you go to the supermarket, the scanner is a laser. Your CD player is a laser. Your laser printer has a laser. The laser printer is actually really interesting. I took one apart not so long ago. I'd been to the Bradford Media Museum and was talking to somebody about how they made televisions in the 1930s. And it turned out that they used devices that are actually very similar to some of the devices that we use to control our lasers. And in particular, what they did is that they had a beam of light that they reflected off a rotating mirror to make the scan lines of the television picture, and then by modulating the intensity of that, you got a picture. Well, it turns out that a laser printer works in exactly the same way. I just think it's fascinating that technology that's around us today was actually exactly the same technology that was around in 1930.
When were lasers invented then?
Lasers were invented around the 1960s. So the first laser wasn't in fact a laser at all. It was something called a maser, where maser stands for microwaves amplified by stimulated emission of radiation.
So why did they use microwaves?
Well, it was easier. It was just easier to do. As I said, it's easier. Microwaves have a much longer wavelength than visible light, so they're, in a sense, the photons are redder. They're so red you can't see them, and it's easier to do. It's easier to make lasers. It's easier to make long wavelength lasers than short wavelength lasers. And then after they'd demonstrated that with microwaves, they were then able to demonstrate it with light. And in about 1964, you get something called the ruby laser. And then that develops into the gas lasers that sort of became developed in the 1970s, which is when I started using them.
So, well, we've talked about lasers in society, but why are lasers so useful in science? You find them in almost, well, any chemistry department you find them in, you'll find the laser laboratory. Why are they so useful?
They're very big. The lasers have two very important properties. Well, actually three properties. They are intense sources of light that you can easily direct. But they also have a property that is known as coherence, which means that they are very monochromatic. It means that they're one color. But this business about being monochromatic means that they're very useful tools for spectroscopy. Spectroscopy is a technique that we use to tell us about the properties of molecules, the shapes of molecules. Molecules are so small we can't see them. So we need some way of measuring their properties, and spectroscopy is the way to do that. And lasers are remarkable tools for making spectroscopic instrumentation, which is what in my lab, that's what we use them for.
So are they particularly useful in, well, physical chemistry, chemical physics, or do they have are they uses for lasers in all science, or is it more of a chemistry thing?
Oh no, they're used all over the place. So communications, you've probably heard of quantum computers. Well, a way of making a quantum computer is you can use lasers to make quantum computers. In the engineering department, they use lasers as a way of measuring what's going on in combustion engines and so forth. I mean, for example, if you imagine an enormous rocket that you're going to use to send somebody into space, and you want to find out a way of figuring out what's happening in the combustion chamber of that, you can't stand anywhere near it. So the idea of being able to direct a beam of light through that flame and measure the properties is a very useful technique.
So you did mention that lasers can be used in your CD players and things. How does that work?
So the idea is that you can encode. If you had a microscope and you look very carefully at your CD, you'll see that it consists of a set of literally little dots, and those, when you reflect light off those dots, then it will reflect well, or it won't, and so you can encode information in that way. And so you need a source of light that you can focus to a small spot, and whose intensity is constant, so that you can modulate it. And that's in that way you can encode information on for example, a disk.
Okay, well, I did ask you about the colour, why most lasers are red. Well, I've seen red lasers, many. I've also seen green lasers, but I've never seen a blue laser. What's so special about a blue laser?
Well, you should take a Blu-ray disc apart, because Blu-ray discs have blue lasers in them. And what's special about them is that the wavelength of blue light is shorter than the wavelength of red light, and as a result, because the wavelength is smaller, you can put more information per square centimetre if you use blue light rather than red light, and that's why Blu-ray discs can show much more information at higher definition and so on. Now, of course, the difficulty was making a blue laser in the first place, and that took some time to do, because, as we've said, it's much harder to make lasers that work in the blue than work in the red.
Lasers were, well, once upon a time used to measure the distance of the moon. Is that still taking place?
It is, in fact. So that's how we know. I think we know the distance from the Earth to the moon to within about a centimetre. And that's because when the Apollo astronauts landed on the moon, they left behind a mirror, and we can bounce a laser off that mirror and measure the time it takes for a pulse of light to go from the Earth to the moon and back again. And because we know the speed of light, we can know very accurately the distance from the Earth to the moon. Actually, there's an interesting experiment. We were talking earlier about quantum mechanics and things like that, and there are very interesting experiments you can do in quantum mechanics, in which you use a laser, and you split it into two beams with a half silvered mirror, and you send one beam one way and one beam the other way, and bring them back together again. It gives rise to a phenomenon known as interference. It's a very particular kind of interference. It's a quantum interference, and somebody in Anton Zeilinger I think he's in Austria, is now trying to do that experiment, but bouncing instead of in the lab, he's actually going to do this quantum interference experiment off the moon by using the same mirrors that the astronauts left 30-40 years ago.
So for all those skeptics that think the moon landings didn't take place, where we're using something on the moon.
It's very strange, though, isn't it? I always find that odd. I remember as a little kid, I sat up all night and watched the first television pictures coming down from the moon. Absolutely amazing. And now to hear people say that it was all a conspiracy is I find really strange.